My name is Ignacio Taboada. I'm a spokesperson for the IceCube collaboration and professor of physics at the Georgia Institute of Technology. I'm very happy to welcome you to this event presenting the observation of neutrinos in our own galaxy, the Milky Way. So we will begin with introductory remarks, and our first presenter will be Denise Caldwell. She's physics director for the Division of Physics at the National Science Foundation.
Thank you very much. The Milky Way seen through neutrinos. The announcement this afternoon describing a new window on the universe and presented by an up-and-coming NSF career for graduate students highlights two major NSF priorities: breakthrough scientific discovery and the promotion of the next generation of scientific leaders. On behalf of the NSF, I congratulate on their achievement, and I'm looking forward to what they are about to tell us.
Thank you very much. And now we'll hear a few words from David Brown, Dean of College of Arts and Sciences at Drexel University.
Thanks, Ignacio. It's an honor to be here today to celebrate this exciting discovery in the field of particle physics, advancing our understanding of the origins of the universe. And we're proud this here at Drexel University to host our esteemed colleagues from the National Science Foundation, the Georgia Institute of Technology, TU Dortmund University, and the University of Wisconsin, Madison, amongst others. Whether in person or on Zoom, thank you for joining us. At Drexel, our most valuable assets, second only to our people, are our partnerships. The IceCube collaboration illustrates how the impossible becomes possible when we seek collaboration on a global scale. My congratulations to all the researchers, including Dr. Naoko Kurahashi-Nielsen and PhD student Steve Scafani. The fact that Steve played such a central role in this discovery is truly representative of our approach to education at Drexel. I would also like to thank the National Science Foundation for their support of discovery and this important work. Thank you.
Thank you very much. And now we turn to TU Dortmund University, and we will hear words from Manfred Bayer, president of TU Dortmund University. Thank you.
Ladies and gentlemen, congratulations. Also on behalf of the Federal Minister of Education and Research, Bettina Stark-Watzinger. Congratulations to all the researchers who contributed to this pioneering work. We know the electromagnetic spectrum, with which our telescopes can see the universe in different light frequencies. IceCube has enlarged this spectrum using neutrinos as new messenger particles. With this very new concept, you have made it possible to explore the Milky Way, gathering evidence that high-energy neutrinos also originate in our galaxy. Thanks to your curiosity and your efforts, we can now see our galaxy with completely new eyes. I'm especially glad about this because we have dedicated the Science Year 2023 to the topic of our universe, and we couldn't possibly wish for a better contribution. This milestone in astroparticle physics would not have been possible without excellent international cooperation. Therefore, I would like to make special mention to the German research groups, and in particular, Professor Helbing and Professor Rode. You played a key role in this major achievement by applying state-of-the-art methods in machine learning. Since 2005, the German Research Ministry has been providing 21.6 million euros for IceCube. And I'm very happy to announce today that we will continue to support research at IceCube in the coming funding period, which actually starts in 2 days. with funding worth 4.3 million euros. That means more budget for more curiosity, more technology, and finally, more science. Perhaps it will enable to learn more about the sources of neutrinos. These are big questions for tomorrow. Today, we celebrate your great achievement. Thank you very much.
So, with apologies, you just heard a pre-recorded video from Jens Brandenburg. He's Parliamentary State Secretary for the German Federal Ministry of Education and Research. We will now hear words from Manfred, President of TU Dortmund University. So please go ahead.
Yeah, thank you very much. Good evening to everyone. We have evening here already, therefore good evening. I hope that you can understand me. I'm actually sick like a dog and start to lose my voice, but I still hope that you can understand me. And nevertheless, I want to welcome you very warmly as president of the TU Dortmund. And I'm very pleased that we can host at least a part of this event today. As a physicist, I actually share your fascination with exploring the universe, even though my astrophysics lectures date back more than 30 years, and I'm actually personally working on condensed matter physics, which I find even more exciting than astrophysics, but this is just a very personal note. I'm extremely pleased that the Dortmund team has been able to participate in the development and in the operation of the IceCube neutrino detector or observatory for more than 20 years now. Today, my colleagues contribute here in the IceCube data analysis, specifically through state-of-the-art machine learning algorithms developed as part of this collaboration. Nowadays, many people are afraid of AI, and some even claim that AI should be stopped. Actually, I'm not afraid of AI. I'm only afraid of stupid AI. And the current result sort of confirms this attitude, at least to a certain extent. Clever machine learning can give us many new and exciting results, and today we celebrate one of these results. So congratulations on this excellent research, which we will learn more about in a minute. And good luck in your future endeavors. I hope that we have an inspiring evening, and I'm even sure that we will have an inspiring evening. Thank you very much.
Thank you very much. So now we will begin a set of presentations describing the result. And the first presentation will be by Naoko Kurohashi-Nilsson at Drexel University. Thank you. Thank you very much. So now we will begin a set of presentations.
Did I go on? Is that okay? Okay. Hello. On behalf of the IceCube collaboration, we'd like to announce the first observation of the galactic plane in high energy neutrinos at a significance of 4.5 sigma. Today we'll present evidence of this, but first let me explain what this means. So, sorry, the feed is, okay, here we go. So, this is a picture at the geographic South Pole where our detector is. The building you see here houses many computers for IceCube. The detector itself is buried under the ice. It's a nighttime photo at the South Pole, and you see this beautiful feature in the sky of the Milky Way. Because this is the South Pole, you see a light green haze, and that's the aurora australis or southern lights. You don't have to be at the South Pole to see the Milky Way. And in fact, for millennia, we have studied the Milky Way. Helen wrote about it. You can fill a history book full of Milky Way observations. It is the largest feature in the sky and well studied. But today, we see it for the first time in something other than a wavelength in light. So the Milky Way is our galaxy. It is a spiral galaxy, and our sun, which we orbit around, is on one of the spirals. If you see it from top down, that's what it looks like. But from edge on, it's flat. So it's like a pancake or a disc. So if you're in the middle of the pancake or disc, looking towards the galactic center, then you would see something like an edge-on disc in the sky. And that is our view of the Milky Way, is the galactic plane. If you take a panel of the Milky Way and center it at the galactic center, this is the panel you see that describes the Milky Way. In recent decades, we have studied the Milky Way in not just optical light, where our eyes work, but we have seen it in many different wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. We have observed the Milky Way using more than just our eyes. And this iconic picture is the multi-wavelength view of our own galaxy. Today, for the first time, we had another image in high-energy neutrinos. This blurry image represents the first time we've seen our own galaxy in something other than electromagnetic radiation. This is an iconic image, as I said. If you're from the Department of Physics or Astronomy, we've seen some version of this poster somewhere in our departments. And because this is our galaxy seen in many different wavelengths, we're very familiar with this poster. And today we add a whole new panel, not just in energies, but in particles. So what are neutrinos? Neutrinos is an elementary particle. So you mean this desk, the air, everything is made up of molecules. The molecules are made up of electrons in the nucleus. And as far as we know, the electrons aren't made up of anything. The electrons are elementary particles. The nucleus is made up of neutrons and protons, which are made up of quarks. And as far as we know, quarks aren't made up of anything. So quarks are elementary particles. Neutrinos are also elementary particles. We think they're not made up of anything. They are what they are. However, neutrinos are not part of what make up you, me, the air, the table, everything around us that we can touch. It is a particle that's emitted when the nucleus breaks, such as in nuclear fusion or fission. Neutrinos are a lot like light. They are neutral particles, as in electromagnetically uncharged, and they're nearly massless. However, unlike light, they seldom interact. So if I have a flashlight and I try to shine it across a board or a metal plate, you would not see the light come out on the other end. That's because the light interacts with the board. If I had a neutrino flashlight, which I wish I did, the neutrinos will stream through because they don't interact, they will stream through, and you will see the neutrinos on the other side of the board. And in this way, we hope to see neutrinos stream out of deeper and denser parts of space. And we hope that neutrinos become a messenger in astronomy where we see different views of space. Let me take a step back and go through the history of what enabled this announcement today. So over 4 decades ago, a neutrino telescope was envisioned in ICE. Amanda, the predecessor experiment to IceCube, was completed in 2000. In 2011, we completed the IceCube detector. The IceCube detector, as I mentioned before, is at the geographic South Pole. So the IceCube laboratory, this picture you saw with the Milky Way is pictured there. When you're standing there, you're standing on top of 2.5 kilometers of glacier ice. It is very high altitude at the South Pole. We have found a way to drill 86 holes in the ice all the way down and leave more than 5,000 digital optical modules, DOMs, or light sensors, in the ice. This way, we have light sensors scattered over cubic kilometer of ice. When you're buried in 2.5 kilometers of ice, you don't see any light. It's pitch black. Until you see a high energy particle zip through. This is real data from the IceCube collaboration. And you can see, let me play that again. You can see as a high energy particle enters, sorry, does not work. When you see a trail of light, that's because of Cherenkov radiation of a high energy particle. Oh, here we go. And in this way, we collect high energy particles in our detector. IceCube is a collaborative effort. As you heard, it's very international. We have more than 350 scientists from 58 institutions in 14 countries around the world. This is one of our collaboration photos. So when we meet twice a year, we take a collaboration meeting photo. This is a recent one. Some of us travel to the South Pole. You can find me in the picture if you squint. And this is a real technological feat as well. If you think about 2.5 kilometers or 1.5 miles from where you're sitting now, think of how far that reaches. We've dug that far down. So it's not just a particle physics experiment, it's a technological feat. Two years after we completed our detector, we found high energy astrophysical neutrinos for the first time from space. We always thought they would come from space, but it took 2 years after detector completion to find it. I was actually tasked to figure out if these neutrinos localized to something in the sky, to trace back to where they're from to see what their sources are. And back in 2013, we couldn't definitively say what created them. Since then, we've identified 2 galaxies that emit neutrinos in 2018 and 2022. Today, we're talking about our third source, our own galaxy. And to tell us what this means and how we did it, I'm extremely proud to introduce Steve Scafani, my former PhD student.
Hi, everyone. My name is Steve Scafani, and I'm excited to be able to talk to you today about the Milky Way galaxy being revealed in high-energy neutrinos. In particular, I want to focus on how we performed the analysis, what the results mean, and why we are seeing the Milky Way galaxy for the first time. This is an image that you've already seen today. We can look at our galaxy in different wavelengths of light. For the purposes of this talk, we're really going to focus in on our high-energy universe. So our high energy universe consists of high energy gamma rays shown here from the Fermilab collaboration and the Fermilab satellite, and our high energy neutrinos shown here now from IceCube. If we wanted to produce high energy particles at Earth, what we do is we take some protons, go to our local particle accelerator, and use magnetic fields to accelerate these charged particles up to very high energies. We can then smash them into some sort of target and produce a stream of secondary particles that we could then study. The same process is happening in our galaxy, just on galactic scales, and at energies 10 to 100 times higher than we can produce on Earth. Cosmic rays are charged particles, which can be accelerated at cosmic ray sources, and we're still looking for the sources of these in our galaxy. But when they interact, they'll produce byproducts of gamma rays and neutrinos that we can observe at Earth. The cosmic rays can also escape the source, remain bound in this churning cosmic ray sea in our galaxy until eventually interacting with the dust and gas of our own Milky Way. This secondary component is diffuse galactic emission, and this is what we were searching for. This would also produce the same gamma ray and neutrino signatures. And in fact, if we look at our gamma ray data, you can see, as shown here by Fermilab, dots along the plane corresponding to gamma ray sources, some of which very well may be the cosmic ray sources we're looking for. In addition, you can see this haze around our galaxy corresponding to where the dust and gas and stuff is. This is the diffuse component that we were searching. So we were searching for neutrinos from this component. So to construct this analysis, what we do is take this image from Fermilab, use what they fit to this diffuse component, and search for neutrinos that correlate with those same directions. We tested a couple of models. The first here came directly from that Fermilab fit, which is shown in the middle. And we also tested two models from other scientists known as the KRA gamma models, so that in total we tested 3 separate hypotheses. In order to not bias ourselves, we define all the analysis parameters beforehand, blind to what our data looks like. And we do this and fix all the analysis parameters until eventually unbinding and looking at what is the correlation between our data and the expectation from these models. When we do so, we see the results shown here. The p-value is a measurement of how likely this is to occur, the probability of this occurring from a random fluctuation of our background data, just by random chance. And you can see for all 3 models, this number is very small, meaning it's very unlikely that our background causes this data. We take into account the fact that we tested 3 separate hypotheses, and we can say that we are seeing 4.5 sigma evidence for neutrinos from the Milky Way, corresponding to the first time we're seeing this signal. Next, I'd like to talk about why we're seeing it now. So the central part of this is we've created a new data set to look for this signal. In IceCube, we have 2 different types of events. The tracks on the left here are produced when a charge current neutrino, when a neutrino interacts, a muon neutrino interacts and produces an outgoing muon. That outgoing muon can traverse through our detector, depositing light along the track. This analysis instead uses cascade events, which are shown on the right. So cascade events are produced from different processes, and they are shown as this spherical blob of light. There are advantages and disadvantages of using cascade events, and I'll go through one of each now. The advantage of the challenge with cascade events is, unlike the tracks, which have a very long lever arm, cascades are the spherical structure. So it's harder to look at that data and predict where the original neutrino came from. On the left here is our angular resolution, or in the y-axis, the distance between the true direction and where we reconstruct that to be for simulation as a function of energy. You can see as we go higher in energies, we are able to reconstruct these events better because we have more information and more data and more light in our detector. But overall energies, we're still somewhere in the range of 5 to 10 to 15 degrees. We've worked with this data set to improve the angular resolution of these cascade events. And in the next talk, we'll go into a little more details about how that was done. The great benefit of cascade events is that they have a lower background. So the plot on the left here is the sensitivity flux, or the number of neutrinos we need to see to start seeing a source as a function of the direction in the sky. From 0 to 1 in IceCube, since we are at the South Pole, we are looking through the Earth into the northern sky. From 0 to -1, we look in the southern sky, which is basically up into the sky in the South Pole. This region has a lot of background for particles produced in our atmosphere. So we see a benefit or a lower number of neutrinos needed to see a source. So the lines are getting lower when we switch from track events to a previous cascade selection, and we see another jump when we switch to this data selection. This second jump is due to machine learning techniques to select more events. Again, we'll go into this in a little more details in the next talk. Another way of thinking about this is, as we're adding more events and as we're reconstructing them better, we are refining our view of the sky. You can see this is resulting in a sharper view. Shown here are the results from 2 searches with 2 years, 7 years, and the new 10-year data set shown in red. And you can see that these views of the sky get more refined and darker as we get more significant. This enabled the measurement that we are seeing today. So just to kind of recap in one slide, we've been looking up at the sky for millennia, observing our own Milky Way in light. And over the recent decades, we've seen this in gamma ray light at the highest energies. We can take the information from gamma rays and use that to predict where our neutrinos should come from. And you can see from this prediction that that is concentrated in the southern sky where there's a lot of background events. We use cascade events to lower this background. And panel D here shows when we account for that angular uncertainty of cascade events, we see two contours corresponding to where we would expect 20% and 50% of the events to come from. We do all this in a blind method to not bias ourselves, and then we look at our data to check the correlation. And what we see that is our data is very correlated to the expectation. This allows us to see the 4.5 sigma and be confident about our measurements. Now that we've seen it, we can start asking a new generation of questions about what are the sources that are capable of accelerating cosmic rays, and can we start to resolve them in the next few years? Next up, I'll pass it to my colleague Mirka Hohenfeld in Dortmund, Germany, and he's going to take a look at some of the details and more technical aspects of the analysis. Thanks.
So yes, thank you very much, Steve. What I would like to do now is look a little bit under the hood of what's happening here in detail. And I want to explain a little bit of how we made this observation possible with the help of machine learning. So before I start, I want to highlight some of the challenges that you encounter in an analysis like this. What we're interested in are neutrinos from the galactic plane, shown here as these orange dots on the galactic plane. And the problem here is that we're really dealing with a needle in the haystack search. So this signal that we're trying to look for is buried in a vast amount of background, so that illustrated by these blue dots. And if you're looking at 10 years of IceCube data, we expect hundreds of billions of these background events. So the real issue or the real challenge here is to try and filter out these few hundred events that we expect from the galactic plane. So what I want to do in the following minutes is to walk you through of how we can do this. And there's two main areas where this is achieved. One is event selection. So this is the process of trying to remove background events while retaining as many signal events as possible. And the other area is event reconstruction. In the above sky maps, you see individual dots. These dots correspond to reconstructed directions. In reality, however, we don't know exactly where these neutrinos come from. So there's an uncertainty associated to them. What event reconstruction tries to do is to minimize that uncertainty. The better we can reconstruct the origin of a neutrino, the better we can get an idea of if it's a signal-like event or if it seems more likely to be background. What's new about this analysis in comparison to the precursor analysis is that we heavily rely on machine and deep learning here. So this is a subfield of artificial intelligence, and you might have come across these applications, these methods in different applications, such as image recognition, autonomous driving, or chatbots. So let me move on and talk a little bit about the event selection. I want to talk a little bit more about the background. So what's shown here is a sketch of the Earth with IceCube at the South Pole. Now, you might be a little bit surprised, although IceCube is a neutrino observatory, the particles that we actually detect with the highest frequency are muons. Muons are a type of particle that are created in air showers in our atmosphere. So that's when a cosmic ray particle interacts in our atmosphere. And we detect these atmospheric muons at a rate of about 2,700 per second. At the same time, in these air showers, there's also neutrinos created. We call them atmospheric neutrinos because they're created in our own atmosphere. What we're really interested in, however, are neutrinos created outside of Earth. So these we call astrophysical neutrinos. These could be astrophysical neutrinos. What we're interested in this analysis is neutrinos from the galactic plane. The problem is for us that most of the neutrinos that we expect from the galactic plane are expected in the southern hemisphere. So this is an area that's dominated by atmospheric muons for IceCube. So one of the major tasks that we have is that we need to get rid of these atmospheric muons. And this right here is an animation showing the principle of how we do that. What we're looking for are cascade events, so starting events in the detector as shown on the right. And the key idea here is that you see the neutrino flying into the detector, and we don't detect any light at that point. Only when the neutrino interacts and creates a particle shower is when we detect light. On the other hand, on the left-hand side, you see a muon coming in. And that muon already deposits energy when it enters the detector. And that's the main feature of how we can distinguish these events. So how does that actually work under the hood? We have a selection of multiple classification and reconstruction methods that are set up in a hierarchical structure. At the very beginning, we have a fairly high data rate with about 2,700 events. These are mostly the atmospheric muons I was talking about. So what we need to do initially is to reduce that data rate with a fast and efficient method. And that's where convolutional neural networks come into play. You might be, might have seen these methods from image recognition. At intermediate steps, we have a lower data rate and can run more sophisticated classification and reconstruction methods. And at the very end, we have about 17 events per day left, and those are the events that go into the analysis. And with these new methods and this new event selection pipeline, we are able to reduce the background by almost 8 orders of magnitude. In comparison to the precursor analysis, this is an increase in signal events that we retain by about a factor of 30. So this is a huge jump. And that's also illustrated here on the left-hand side. So on the y-axis, you have the number of astrophysical neutrinos that we expect from the southern hemisphere. And on the x-axis, you have the energy. This dark curve is this work here. And you can compare that to the light blue curve, which was the precursor analysis. And you can see that there's a big jump in these two curves, and that's due to these new methods corresponding to the 30 times as many events. Now, moving over to event reconstruction, the second area where we improved on with machine learning. We've seen event views like this before in Naoko's and Steve's talks. What I want to do now is to go into a little bit more detail of what's actually happening here. So we see the spherical energy deposition, and what's happening here is that a neutrino somewhere within that spherical energy deposition interacts with the ice and a particle shower is generated. These secondary particles will emit Cherenkov radiation, and you can think of this as a bluish shimmering light. And this blue light is what we detect with our highly sensitive cameras. The actual data, the way it looks like for us, is then current over time, as shown on the top right. Now, the task of event reconstruction is to try and infer the properties of the neutrino. So what energy did the neutrino have? Where did it come from? And the way we do that is by looking at the patterns in how light was distributed in the detector. And in this particular analysis, we developed a new method to reconstruct these events. And this is a combined approach using deep neural networks and maximum likelihood estimation. So what is the maximum likelihood estimation? I'll try to walk you through that in a simplified manner. So we have this event view on the bottom left, and we already said we have a broad idea of what's happening here. So there's some neutrino interacting with the ice. This idea of what's happening, we can also call an hypothesis or an event hypothesis. What you now do in maximum likelihood estimation, based on this event hypothesis, you can compute what you would expect to see in the detector. So that's shown in these bottom right plots, these three. And what you do now is to compare that to the data you observed. So the expectation here are these gray curves denoted by lambda. And what we actually observed are these black dots. And what you now do in maximum likelihood estimation is that you retune your hypothesis to best match data. So you can see, for instance, on the bottom right, the expectation curve doesn't really match the observed data here. So in an iterative process, you update this hypothesis until you best describe your data. And this final event hypothesis is the reconstruction result. Now, what's new in this reconstruction method is the way in how we compute the expected light yield. And this is done via a neural network. To the experts on the call, this allows us to model the underlying high-dimensional probability density functions in a highly efficient and accurate manner. And it also, with the approach via neural networks, allows us to exploit available symmetries and domain knowledge that is not really possible in convolutional networks or graph neural networks and things like that. So with all of this together, we have an improved resolution over the energy range, over the entire energy range, as shown in this plot here. So Steve showed a similar plot earlier. On the y-axis is, again, the opening angle between true and reconstructed direction, and on the x-axis is the energy. What's shown here, so first of all, the lower the curve, the better the angular resolution, the better we can reconstruct these events. Because of this new method, shown here as a dark line, we can improve upon the old reconstruction methods shown in the other lines because we're avoiding simplifications and because we're better utilizing information. Now, if you combine that with the improved event selection, so the 30 times as many events, we improve upon the precursor analysis sensitivity by a factor of 3. If you're not familiar with sensitivities, you can also put this in terms of different numbers. So in physics, often you can improve an analysis by simply taking data for a longer period of time. If we had taken the old analysis and just run that for an additional period of time, we would have had to run for an additional 75 years to achieve the same improvement in sensitivity. So not only do we save 75 years of lifetime due to these novel methods, but we also save upwards of $500 million that it would take to run that it would cost to run the experiment for so long. So with all that put together, we have described new methods that really improve this analysis. And you might ask, well, how can we trust these methods? How can we know that what we see is real? And I think that's really what the beauty is about this analysis, is that it's using a data-driven approach. So we're not relying on any simulation to model our backgrounds or compute the significance. And I'll try to explain briefly on how that works. So just to remind you, we're looking for correlation of neutrinos based on these model expectations as shown here on the left. This is an expectation derived from Fermi-Lat measurements. And what we use in this approach or exploit is the fact that the Earth rotates with time. So all of our methods only ever see the local coordinates. Sorry. So we only see the local coordinates, and we can use the fact that we just randomly assign new times to events, and that essentially scrambles events on the sky just because of the rotation of Earth that changes. So if you take this original template here and you just randomize the event times, you arrive at our background distribution shown here. So this is how we model our background. And we can do the same thing to now compute the significance of our analysis. So we take our data set, randomize the times of events, which is equivalent to just randomizing the locations on the sky. And then we perform the whole analysis. We compute how correlated these events are with the hypothesis. And this correlation we also refer to as a test statistic value, or lambda, shown in the upper right histogram. For the experts on the call, this is a likelihood ratio test that we're performing. And you do this over and over and over again. In this analysis, we ran this hundreds of millions of times. And once you have this distribution built up, you can get a feel for how likely it is to arrive at a specific test statistic value by random chance. So if you now look at our analysis results, so that's shown here on the left plot, you have here in the dark solid line, the analysis results. So we have a test statistic value of 22.19. So again, this is sort of, you can think of it as the correlation of strength. And in the background, you see this histogram of our pseudo experiments. And you see that it's highly unlikely to arrive at such a high correlation just by random chance. And this corresponds to a global significance of 4.5 sigma. On the right-hand side is a visualization of what this test statistic looks like on the sky for each of the 3 tested galactic plane models. And you can see that in each case, we have a clear signal from the galactic center region and corresponding to the contours as tested in these models. So let me summarize and emphasize again that this observation was made possible by these novel developments in methods. And with that, let me hand it off to Wolfgang Rode.
Thank you very much. One is always asked why we are doing all this. And therefore, I want to look at this from the point of view of the connection between cosmic rays and neutrinos. Cosmic rays were discovered more than 100 years ago, and exactly 100 years ago, Kohlhorst did the first under ice investigations at the Eiger Glacier in the Alps. We know that cosmic rays are atomic nuclei. In the meantime, we have measured the energy spectrum, and we know from energetic reasons that the overwhelming part of the cosmic radiation stems from our own galaxy. Only a few particles reach us from other locations. Detectors like IceCube, which are triggered 1 million times per square meter, and here are obviously mainly triggered by events from our galaxy. However, atomic nuclei are charged, and charged particles lose all their memory about their origin in the magnetic fields of the universe. So the particles themselves are not appropriate to trace the cosmic rays backwards. For this purpose, we need neutral particles like neutrinos, or high energetic gamma particles, which are produced at interactions of the cosmic rays closer to their origin. However, gammas may be also produced by movement of electrons in magnetic fields, so that's a picture of the galaxy in the gamma ray, which one used to get a handle on the magnitude of neutrinos which are produced in the galaxy is not unique. So the single messenger particles pointing directly backwards that are neutrinos. Therefore, in the 80s, far-sighted colleagues around Francis Halsen started to think how to set up a neutrino telescope at the South Pole. The technology was explained, and I want to remind you that we have two relevant signatures in this detector. The one are track-like signatures stemming from muons, heavy electrons, passing through the detectors, which seem to carry a wonderful directional information. Others are more spherical and apparently not so well appropriate to do directional reconstructions. In the first 20 years, when one investigated in the neutrino flux, one concentrated on astrophysical muon neutrinos, and what was measured was the clear signal of this component covering 20 orders of magnitude without any deviation from the expectation of atmospheric origin of these particles. Only in the year 2013, when IceCube was finished and the first data were analyzed, we see on the right side a clear indication that the data covered in detector parameters more events than expected from the astrophysical component. At that time, one knew that one had discovered the astrophysical neutrinos. However, one did not know where they come from. But one knew that they are probably visible at high energies. Therefore, one followed the track of high energetic neutrinos by looking at the point of their origin with Cherenkov telescopes, and was lucky in the year 2017 when one was able to see the muzzle flash of a neutrino source. This was AGN TXS0506, where one then had discovered the neutrino and the corresponding gamma radiation at the same time. Last year, all data of IceCube were taken, and in a list of 110 sources, one looked whether certain source positions would stick out from this list. And one discovered again an active galaxy, this time NGC 1068, is very clear source of high energetic neutrinos. Now one had two neutrino sources. However, both of them were extragalactic. What's happening with our galactic neutrinos? The problem is that, as we have heard, the galactic plane is south from the IceCube detector. This means that the neutrino signal is reaching the detector from the same direction like the cosmic rays, which do interactions and produce a very huge background in atmospheric interactions. The problem is then obvious. Those wonderful track-like events which we use to look at the signals are now covered by a huge background from atmospheric muons. So that our primary signal was suddenly not anymore the best signal, but it was left over was a cascade-like events, which obviously have no background because they are produced in the detector. The problem here was that it were first only so few events that one could not hope to see the signal of the galactic plane. This was a situation where the analysis which was described before came into the game, and with the power of machine learning, one was able to enhance this signal so much that one could set up the right filter to look at the sky. And doing so, one could move, so to say, at the position of the Earth and look at the sky, turn the filter around, and what you see on this plot is an overlay between the neutrino signal and the optical signal of the galactic plane. So after having now seen with this method the fingerprint of our galaxy, one might ask what we are hoping to do next. The first problem will be to solve the Galilei question, to see singular sources in this smeared out fingerprint on the sky. So the question is how many supernova sources contribute to the signal. The next question will be whether the up to now not taken into account signal from the track-like events might contribute to this signal. These are things which we are going to do in the very near future, but it is obvious that we will hope to enlarge the detector to improve the quality of our events and to obtain a larger amount of data. We will have to improve our theoretical knowledge about the galaxy, leading to a better simulation of the universe, which we need to improve further the methods of machine learning, which we have applied and will further apply. So we did this in a wonderful collaboration of IceCube from more than 350 people from 14 countries, which have contributed to the experiment and the data collection. And of course, we were supported by funding agencies like they were depicted here, which made our life as physicists possible, for which we are very grateful. So I thank you very much.
So thank you, Wolfgang, and thank you to all the speakers. So this part concludes the 4 presentations. I will now start panel discussion. We will take questions. And besides the 4 speakers, I welcome Albert Carle from University of Wisconsin at Madison. So let me begin asking if there are any journalists here in this room at Drexel that would like to self-identify. Okay, any journalist at TU Dortmund, please. Okay, very good. Thank you. Then we'll start with a couple of questions here in person at Drexel. So if anybody would like to raise a hand, please.
Thank you so much. Really great work. I was wondering if you wanted to investigate how you could improve the directional information you get as an additional way to improve the maps you're creating. Is that a way, is there something you can do and improve on that front as well?
Perhaps that Mirk Hundfeld can take that question, please.
Just to make sure I understood the question correctly, this is regarding if we can better reconstruct the neutrinos, the direction, or?
Yes, the direction from the cascades.
So we did part of that in this analysis. We did on the event selection side, but also in the event reconstruction. We had this hybrid method that uses deep learning and maximum likelihood estimation together. But nevertheless, even with those methods, we were able to do major improvements. But there's certainly more that can be done. I personally am pretty excited about the IceCube upgrade coming in the next few years, because that will help us pin down systematics that are currently limiting our resolution at higher energies. So there will certainly be improvements coming in that front in the next few years.
Thank you. And we had a second question here in this room, please.
Hi. I was curious if there were other astrophysical sources within the Milky Way that could be sources of neutrinos beyond just the disk, but I don't know, like globular clusters outside of the disk, or is it something that this method can be used to investigate, or is it mostly just the disk because of its the population of neutrinos coming from that? Thank you.
So perhaps Steve Sclafani can take this.
Yes, thanks. So right now with our angular resolution, we're not able to pull apart. We know that there are sources of neutrinos in our galaxies, and we're trying to identify them. They could be, galaxy cluster. They could be globular clusters or supernova remnants. People have ideas for these. With this analysis in the angular resolution, we're not able to, but we can think about it like the first step. Now that we've seen neutrinos from the Milky Way, the next kind of big question is, okay, how do we disentangle these two things, the diffuse component and the sources themselves? And, eventually we hope to be able to get an image like we can in gamma rays, where these things are very obviously separated. Thanks.
Thank you. So perhaps we could take a couple questions at TU Dortmund. So if we could have the first question, please, over there.
How many events have you seen from the galactic plane with sources, and is the energy just above 1,000 TeV or 5 TeV?
Thank you. Maybe Naoko Kurahashi-Nelson can take this. You prefer Steve to take this question. Sounds good.
Okay.
Take that question.
So we tested 3 different hypotheses, and each of those yields a different number of best fit events. So depending on what signal we're looking for, what concentration, and as you say, what energies we're looking at, that number can change. So all of these are in the hundreds. It goes from about 200 to about 750 events that we're detecting. That is the best fit number of signal events from the galactic plane. And the energies we're sensitive to are in the TeV ranges from a TeV to, up to about 100 TeV. And we have a plot in the paper that shows those energy ranges.
Thank you. Another question at TU Dortmund, please.
I'd like to know how big the data sets were you used to train the convolutional networks for selecting the events.
So perhaps that would be for Mirko Honfeld, please.
Yes, so it's in the multiple millions. So for the simulation, yeah.
Thank you. And could we have one question from the online chats?
Yeah, there's a lot of great questions. I'll focus on a more technical one. There's several people who want to know about the flux. What does the energy spectrum look like? Do you see anything that looks like a pion bump, as if neutrinos are coming from ion decay?
Perhaps Naoko, you would like to take this one?
Yes. We haven't tested is the correct answer. And there's a good reason we haven't, because as Steve and Mirko were talking, we do a blind analysis. We get one shot at testing this. So we want to make sure our hypothesis is correct before we test it. If we look at the data and tune the hypothesis, it's very biased. So we will be doing those studies. We will be looking for the energy spectrum on its own. The only thing we've done this time around is to fit for a model, test a model hypothesis, even in energy spectrum. And that'll be future work. I think the first follow-up work would be to individually test the energy spectrum that we see from this emission and see if there's deviations from power laws and things like that. Would be fantastic to do in the next couple of years, I think.
Thank you. So let's see if we have another question here at this auditorium at Drexel.
Hi, I was wondering what the future of this analysis looks like. You say that, you have planned upgrades in the future. What kind of sensitivity increases do you expect from that?
Perhaps Albert Carla can take that.
Thanks for the question. And I think it's amazing how IceCube, even though it's frozen in since more than 10 years, it's a living detector and it improves digitally. You can still improve the resolution digitally. And as Mirko has pointed out, and this is a prime example, this result. And so the question is, how much more can we tune? And I think there's still a few more ideas in the plan. And one is the upgrade of 7 strings in a little more than 2 years from now at the South Pole that will help us to even better calibrate our instrument. But at the same time, this does have its limitations. At some point, we'll need a bigger detector. And there are plans underway to build a detector that 10 times would be 10 times larger in volume and have about 10 times the coverage of the 5,000 sensors that are in IceCube. And so that at some point will be a larger detector would be needed. But we still are not at the limit, even with the existing IceCube, with this work.
Thank you. Maybe have another question at TU Dortmund that is in person, please.
Could your methods be used to improve other experiments as well?
So perhaps Wolfgang Rodi can take that question, please.
Of course. Yeah, what we use are machine learning methods which are so general in their application that they can easily be used not only in other experiments of the field of astroparticle physics, but also in the field of particle physics and also in industrial environments. The way in which they are used are very similar. The practical importance is different from application to application, but there is one common property in this, that is that a lot of resources are saved if one does this calculation correctly.
Thank you. So perhaps one final question from online, please.
This one might also make you uncomfortable, but there's questions about what looks like some of the clumpiness in the maps that you show. Any comments about potential correspondence with sources that we think we might know about?
Let me read that to Naoko again, please.
No comment. But stay tuned.
Okay, so thank you very much for having tuned to this event. We're definitely very excited of this new result, which joins previous sources from the IceCube collaboration. And until next time, goodbye.